In this video, we're going to talk about a specific type of random variable called a binomial random variable or a Bernoulli random variable. These random variables have a specific type, so they have a lot of properties that are the same, and nicely they satisfy some formulas, so it's easier to compute the expected value and also the probability for each output of our random variable. So let's start. So let's talk about when these might happen. So when we have an experiment consisting of performing the same sort of mini experiment where you do it multiple times, okay, then we might use a random variable to count how many times a certain outcome occurs. Okay, this is a common type of experiment. So an example that we saw before was flip a coin multiple times, okay, maybe 100 times, okay, it could be as many times as you want. And in the last video, we were counting the number of heads that occurred. Okay, you might roll a die multiple times, okay, 50 times, and count the number of sixes that you roll or something. Maybe you want to do a survey. Okay, so maybe you survey 100 people on their whether or not they were able to work from home. During the quarantine. So then you might want to count the number of people that were able, or something like that. Okay, so each of these things you're doing, so the same sort of mini experiment. So in the first one, the mini experiment is to flip a coin or roll a die, or the survey is each person. Okay, each of the 100 people, you're asking them a question. That's the mini experiment. Okay, so these type of random variables are the focus of this section. Okay, they have many similar features. So some terminology. Okay, so the mini experiments are called a trial of the experiment. And when they have two possible outcomes, so we normally refer to them as a success and as a failure, but the success might be a bad thing. Okay, so the success could be exhibited side effects from a drug. Okay, when we're trialing a drug or something. Okay, but they have two possible outcomes, so you could group as success or as a failure. Then we call it a Bernoulli trial, or I normally like to use binomial trial. We use little p to be the probability that success happens in a single trial, and q, which is going to be 1 minus p, is the probability of failure in each trial. I already said this, so success doesn't have to be a good thing. Okay, it might be selecting defective objects or something. So when you have a sequence of n trials, so that's one trial, or so trial after trial after trial, n times, we call it a binomial experiment or Bernoulli experiment if there are two possible outcomes in each trial, so success or failure. So that means each trial is a binomial trial. Okay. The probability of success, p, is the same in each trial. Okay, so it doesn't change. And the trials are independent. Okay, now if p is the same each time, then that usually means the trials are independent. But those are the three conditions. So that makes a binomial experiment. And then if our random variable x counts the number of successes in this binomial experiment, that's when we call it a binomial random variable. Okay, so that's a lot to take in. So let's do an example. So consider the experiment where we roll a die 5 times. Okay, x is going to be the random variable that counts the number of sixes that occur. So I'm first asking, is this binomial? Is this a binomial random variable? You probably think yes, because I gave basically this as an example of a binomial random variable. But let's check the conditions. So, how many trials do we have? So how many mini experiments? So the mini experiment is rolling the die, okay, and we're doing it 5 times. So we have 5 trials. Okay, so that's our little n. Okay, so our little n is 5, so that's our n trials. So in each trial, what does it mean to be a success? Okay, well, we want our random variable to count the number of successes, and our random variable is counting the number of 6s. Okay, so we probably want a success to be roll a 6, which means that failure, okay, is the opposite, so not roll a 6. It's okay that the failure has multiple ways to happen. Okay, so it could have, you could roll a 1, a 2, a 3, a 4, or 5. Okay, all of those are not 6s. But because you can group it in either you roll a 6 or you don't roll a 6, it's still a binomial trial. Okay, so each trial has 2 options. Okay, so this makes it a binomial, okay, trial. Okay, and also x is counting the number of successes now. Okay, so that's good. Our p, little p, so this is the probability of success. So when I roll, I have a 1 out of 6 chance to get a 6. Okay, so q is going to be 5 out of 6. And these are the same for each trial. Okay, this is actually because the trials are independent. But when we roll one time and then we pick up the die and roll again, the die doesn't know what it did the time before. Okay, so the probabilities will stay the same. So our trials are independent. And the probability is the same each time. So we can finally conclude, yes, x is a binomial random variable. Here. So what if I wanted to compute the probability of rolling exactly 2 6s? So using our notation from the last, from when we introduced random variables, this would be the event that our random variable equals 2. So it's counting the number of successes or the number of 6s, and we want to get exactly 2 6s. Okay, so that means I should have counted 2. So we want to have a uniform sample space so that we can say this probability is the number with exactly 2 6s divided by the number in the sample space. So we're rolling, so let's talk about the sample space here. So what I'm going to do, we have how many die? We're rolling a die 5 times. So each time we roll, 1, 2, 3, 4, 5. Each time we roll, there's 6 options that the die could give. So our sample space is going to be 6 to the power 5. Okay, so 6 times 6 times 6 times 6 times 6. I think that was 5 times. Now, for the event, it's a little bit harder. 2, 3, 4, 5. Okay, so here's our die. Okay, so this is sort of roll 1, 2, 3, 4, 5. Okay, so what we want to do is we want to get exactly 2 6s. Okay, so we need to know where are the 6s. So how many ways could we select where the 6s are? So on which roll did we get a 6? So from the 5 rolls, we want to select 2. Okay, so this is which roll was a 6. So let's say that we do that and we know that it's roll 2 and roll 3 that are going to be the 6s. Then because they have to be 6s, there's only one way to get a 6 there. Now these other rolls that are left over, because I'm getting exactly 2 6s and I already have them, they cannot be 6s. So that means there's 5 options for each. Okay, so this is going to be 5 choose 2 to pick where the 6s are. Make them 6s. So there's 1 squared. Okay, so make 6s. And then we're going to have to multiply by 5 cubed. So this is 5 options for the other 3 rolls. Okay, and now I'm just going to rewrite that here. So 5 choose 2 times, oops, not 5. So 1 to the squared we don't really need, so 5 times 5 cubed. So I didn't actually compute this, maybe I should. So we have the number, but what I want to do is rewrite this. Okay, so if you compute this, you should get 0.1608 approximately. Okay, but what I want to do is actually rewrite from here. Okay, so, or I'm going to take the 5 choose 2 down, okay, and then I'm going to group the other things. So notice on the top, I have 2 1s and 3 5s. So that's 5 things in total. And on the bottom, I also have 5 things. So what I'm going to do is just group them. So I'm going to have 1/6 twice, and then I'm going to have 5/6 3 times. Okay, now you might notice that 1/6 is actually P, and 5/6 is actually Q. And this 2, the P happens 2 times. That's what we're looking for. So we want, this is X equals 2, right? We wanted the probability that we get 2 successes. Okay, so this actually is where the formula for this, this is how the formula looks for computing when you know the random variable is binomial. So it's very helpful to be able to determine when it's binomial or not, because you get these formulas. If you know it's binomial, you're able to use these formulas. So if X is a binomial random variable, okay, with n independent trials, probability of success P, so that means Q is 1 minus P. Then if we want to compute the probability that we get, so this is exactly, okay, K successes, okay, whatever that means. What we can do is do n choose K times P to the K times Q to the n minus K. Okay, I'm going to try to explain each of these. So, n choose K is select K trials, so K of the n trials, to be successes. Okay, P to the K, because they're independent, you want those trials to be, so let's say it's the first K. You want trial 1 to be a success and trial 2 to be a success and etc., etc. So you're computing the intersection. Because they're independent, that means you can multiply the probabilities. So the probability trial 1 is a success is P, times the probability trial 2 is a success is also P. So this is the probability, the selected selected k trials are successes. Okay, and then the q to the n minus k is the probability that the remaining n minus k trials are failures, because we want exactly k successes. So we don't want more than k successes. So that's where the pieces come from, but this is a formula that you can use when you know you have a binomial random variable. Another really nice formula that we get is if you want the expected value for a binomial random variable, it's just the number of trials times the probability of success. So this is really useful because now this is the only case in this class where we don't need the probability, that's not a B, the probability distribution table to find the expected value. Okay, so if you're doing a lot of trials, so like 100 trials, your probability distribution table is going to be huge. So you wouldn't want to need to compute that all the time, and the binomial random variables are nice because they allow you to skip that step because you have this formula. So let's do an example. So suppose a drug has a 0.03 probability of having side effects, and we give it to 100 people. Okay, so we want to define a random variable and check whether or not it's binomial. So the thing that I care about is how many people have side effects. So I think I want my random variable x to be the number of people who have side effects from the drug. Okay, so that means that my number of trials are the number of people. Okay, so there's n equals 100 trials. So each mini experiment is giving the drug to each person. The probability of success here, which is actually having side effects, they give me is 0.03. And this is the same for each person. Okay, so that means I'm going to have independent trials. Q is going to be 1 minus 0.03 or 0.97. Okay, success is going to be has side effects, so that X is counting the number of successes. Okay, so failure is actually a good thing here. It means no side effects. And the trials are independent, because if one person has side effects, the next person it's not going to affect the chances the next person has side effects. Okay, so X is a binomial random variable. Okay, so that's good. Now, it wants to know what is the probability exactly one person taking the drug experiences side effects. So what we're looking for here is the probability that capital X equals 1. Okay, well, we have a binomial random variable, so we can use the formula. So it should be, so our n, okay, maybe I'll write this on the side. So n is 100. Our k is 1, that's the value that we're interested in. P is 0.03, and Q is 0.97. So it's going to be 100, choose 1, times P, so 0.03 to the power 1, times Q, 0.97, to the 100 minus 1. Okay, so this I'll just write again. Okay, so 0.03, I don't need to write the 1 really. And then 0.97 is going to be to the power 99. Okay, if you compute this, you should get 0.147 approximately. Now notice these powers, okay, the one that's missing here, but these exponents add to 100. Okay, that's the number of trials. Okay, that's good. So they always should add to the number of trials. So let's try another one. What is the probability at most 2 people experience side effects? So we can also, so this is at most, okay, that's slightly different. So that means that this event is actually x is less than or equal to 2. So now we want to be careful. The formula that we have is for equals, okay? Not less than or equal or greater than or equal or greater or just equals. So what we need to do is split this into cases so that we have equality. So the only way that x is at most 2 is if x is 0, or if x is 1, or if x is 2. So we can add up those probabilities. We already did 1, but I'll just do it again. So, and we can use the formula now for each. So 100 choose 0, 0.03 to the power 0, 0.97 to the power 100 minus 0. Actually, so we already did 1, okay, so this is 0.147. And now I want to do the 2 case. So 100 choose 2, 0.03 to the power 2, 0.97 to the power 100 minus 2. Okay, so 100 choose 0 is a 1. Okay, so this is a 1. Okay, anything to the power 0 is also a 1. So this first one is actually just 0.97 to the power 100. Okay, we already did the 1 case. So now I'm going to have 100 choose 2 times 0.03 to the 2 times 0.97 to the 98. Okay, again, notice these exponents add to 100, the number of trials. And if you compute each of these, you get approximately 0.0476 plus 0.147 plus 0.225, which is going to be 0.4196 approximately. So if you have a less than or equal, or you have an inequality, what you want to do is think about the equality version. So cases, you might also want to use the complement rule sometimes. Okay, let's try another one. Here, you know at least one person exhibits side effects. What's the probability that at most 2 have side effects? So this is a conditional probability. So we want to know the probability x is at most 2 given that x is at least 1. So let's use the formula for conditional. So it's the intersection of these 2 divided by the one that we know happened. Okay, now people often get confused about these intersections. Okay, so we can go 0 to 100. And we want both of these to happen. Okay, let's do a highlighter maybe. So if x is greater than 1, that means that I'm 1 or bigger. So it's all of that. Okay, if x is less than or equal to 2, it means that I'm 0 to 2 only. So where do these overlap? Well, they have to be either 1 or 2. Okay, so this is the same. Oops. This is the same as saying the probability that x is between 1 and 2. And if I'm greater than 1, I have so many cases, so I'm going to do the complement, which is going to be less than 1, which is just 0. Okay, now you can split up the top even more to be x equals 1 plus the probability x equals 2 over 1 minus the probability x is equal to 0. Now we've actually computed all of these already. So probability of x equals 1 was 0.147. Probability of x equals 2 was 0.225. And then the probability of x equals 0 was 0.0476. Okay, so if you compute this, you get 0.391. Lastly, how many people do we expect to take the drug, who take the drug to expect to have side effects? This is E of x. Because we're binomial, this is just n times p. So 100 times 0.03 is actually 3. Okay, so here we got an output for x, but you don't have to. So we expect 3 people to have side effects, okay, on average. Okay, one more example, and here we just want to think about whether or not this is binomial. So we have a box of 10 light bulbs that contain 2 defective light bulbs. You select 3 bulbs at random, okay, one after the other without replacement. And x is the number of defective light bulbs we get. So is x binomial? So our trials are going to be selecting light bulbs, which means that I'm going to have 3 trials, so n is 3. On each trial, there's a success. Okay, so that means x is counting the number of defective light bulbs. So this success has to be select a defective one. Bulb. Okay, so that means that failure is select a working one. Okay, so we have binomial trials. Okay, a binomial trial. So now we want to think, okay, what would P be? So the probability of selecting a defective bulb, okay, on a single trial. So how would we compute that? So on the first trial, before we've selected any bulbs, before we've selected any bulbs, we know that P, there's 2 defective ones out of 10 in total. So P is going to be 2 out of 10. Okay, but once we select, okay, but in future trials, it depends what we picked before. Because we're not replacing them. So that means P changes and the trials are not independent. Okay, so here is an example where x is not a binomial random variable. It's as close as you can get to 1, essentially, okay, but it's not binomial. If for some reason you did it with replacement, okay, so where you put the bulb back in, then your probability is going to be the same each time,